Hello, and thank you for viewing my presentation. My name is Matt Patterson, and I'm a postdoctoral researcher at the University of Oxford in the UK. Today I'm going to talk about how Southern Hemisphere atmospheric circulation is likely to change under climate change, looking at the end of the 21st century. In particular, I'm going to argue that changes to wave forcing from low latitudes can successfully explain the zonally asymmetric changes seen in CMIP5 models. To provide some motivation for this talk, why are changes to atmospheric circulation important? Well, precipitation is a variable of considerable importance to society, and any changes to precipitation patterns, whether that be an increase in heavy rainfall and thus an increased risk of flooding, or else reduced precipitation and an increased risk of drought, these could have a substantial impact on society. Now, in order to make projections of precipitation changes on a regional scale, for instance, for places like New Zealand and Australia, we need to understand how jet streams, cyclones, and other features of atmospheric circulation will change. Now, this talk will focus on the Southern Hemisphere winter. The reason to focus on this one season is that the dynamics of circulation change are quite different between different seasons. These figures show the change in upper level zonal wind in colours in Southern Hemisphere winter on the left and summer on the right, between a high greenhouse gas emission scenario and the present day. These figures are multi-model means across the CMIP5 ensemble. In summer in recent decades, the jet has shifted polewards at all longitudes, mainly as a result of ozone depletion, and on the right we see a similar pattern in future projections as a result of greenhouse gas emissions. On the other hand, changes to the winter circulation, shown on the left, are much more zonally asymmetric, and stationary waves play a larger role. In particular, there is an increase in the westerlies to the south of Australia and a strengthened subtropical jet over the eastern Pacific. Given the larger role of stationary waves in winter, we will now focus on the stationary wave response to climate change. This figure shows the climatological mean stationary wave pattern in CMIP5. This is dominated by zonal wave 1 patterns in the mid to high latitudes, largely as a result of zonal SST asymmetries in the tropics, including the warm Indian and Western Pacific Oceans. These SST asymmetries generate a stationary Rossby wave which transports energy polewards. Colours now show the multi-model mean change in the stationary wave pattern between the late 21st century and the present day. Notable features are the cyclonic anomaly in red to the south of Australia, the anticyclonic anomaly in blue over southern Australia, and the cyclonic anomaly to the west of southern South America. But the question is, how consistent is this pattern across models? In particular, changes to tropical sea surface temperatures are relatively uncertain looking into the future. So is this pattern dependent on the structure of SST change? One way in which we can examine this is with atmosphere-only model runs. We use the AMP4K simulations, which have SSTs uniformly raised by 4 Kelvin in comparison with the present day. These plots compare zonal mean temperature changes between fully coupled runs and the atmosphere-only simulations, and show that many of the salient features, such as tropical upper tropospheric warming, are present. Now, comparing the stationary wave patterns seen in both coupled and atmosphere-only runs, it can be seen that the patterns are remarkably similar. Moreover, hatching indicates where 80% of models agree on the sign of the change. Stationary wave patterns in models are clearly responding in a consistent way to climate change, and this doesn't depend on the specific pattern of SST change. However, inevitably different SSTs will modify some of the details. So for instance, the AMIP runs, shown in the bottom right, emphasize an anticyclonic anomaly over the eastern Pacific, while the coupled models in the top right emphasize a cyclonic anomaly to the south of that. If we now think about this from a theoretical perspective, how may stationary waves change under climate change? If we consider a simplified barotropic framework there are two main ways in which stationary waves can change, either through changes to the location or the strength of the Rossby wave sources, and that may arise because of changes to diabatic heating, or secondly through changes to the basic state winds, as the propagation of waves is sensitive to the structure of atmospheric waveguides. In this talk, I'm going to focus on the former mechanism and argue that changes to tropical Rossby wave sources can explain many of the changes that we see to circulation in the extratropics. These figures show the climatological Rossby wave source in CMIP 5 on the left, and the change in the Rossby wave source in the end of 21st century runs on the right. Once again, hatching indicates where models agree on the sign of the change. In general, it appears that the Rossby wave source weakens at most locations in the tropics and subtropics. This is consistent with the general weakening of low-latitude overturning circulations projected by models, and these changes appear to be strongest and most consistent across models over the eastern Pacific, as shown by this red circle, while there is little change on average over the Indian Ocean. We now examine the effect of changing the Eastern Pacific Rossby wave sources through a multiple regression analysis across the model ensemble. First, we average the Rossby wave source across the two boxes shown here over the South Pacific, a northern box and a southern box, and regress this back onto the Rossby wave source field. Note that these patterns are not significantly correlated. Next, we regress these indices onto the stationary wave change across the models, and the associated patterns are shown here. If we then combine these patterns by multiplying each by the mean value of the Rossby wave source change and adding them together, we can attempt to reconstruct the full stationary wave pattern change. Remarkably, this closely matches the full pattern change in both magnitude and structure, and this suggests that the Rossby wave source changes can explain the stationary wave change in the multimodal mean. We can further test this mechanism using a barotropic model. Let's begin with the barotropic vorticity equation with linear damping and hyperdiffusion. Next, we add a term which forces the basic state to exactly match that of the historical climatology on a given pressure level for a given CMIP 5 model. Following this, we add the Rossby wave source change between the projected future and historical runs in just the tropics and subtropics as seen in the figure on the right. Here we have actually just added the Rossby wave source over the Pacific, though adding the Rossby wave source at all longitudes gives similar results. We then allow the model to evolve and the solution becomes steady after about 2 weeks. Here we show results from 4 different CMIP 5 models. However, we have also performed this for 31 other models with similar results. On the left is the full RCP 8.5 difference from the historical simulations with the corresponding barotropic simulation on the right. Whilst not all of the details are captured in the barotropic simulations, this simple technique is able to represent the main features of the full stationary wave differences in RCP 8.5. Beginning with the BCC model in the top panels, the barotropic model fails to capture the correct centres of action from the full model, but it does successfully show the zonal wave 1 response in mid to high latitudes. Looking at the other 3 models, all are able to capture the cyclonic anomaly in red to the south of Australia and the anticyclonic anomaly downstream of that near West Antarctica. The success of this technique builds on the evidence of the regression analysis, confirming that southern hemisphere stationary wave changes with climate change can be successfully modelled using barotropic Rossby wave dynamics. We can gain further insight into the nature of this wave pattern by considering the development of the pattern in the barotropic simulations associated with the AMS2021 model. Other models show many of the same characteristics. After 1 day, it can be seen that a pair of anticyclonic and cyclonic anomalies have developed over the subtropical South Pacific. Subsequently, a Rossby wave train develops downstream into the Southeast Pacific, while the cyclonic anomaly in the subtropics spreads eastwards. On day 3, the cyclonic anomaly in mid-latitudes develops something like a tail, which becomes a large-scale zonal wave 1 pattern, and this propagates westwards at high latitudes. Note that westward propagation of Rossby waves is only possible for very low wave numbers. As we continue to step through the evolution of the pattern, this cyclonic anomaly strengthens and breaks off from the original cyclonic anomaly, and after a couple of weeks, the pattern remains stationary with a slight strengthening over the succeeding days. Conclusion. Understanding atmospheric circulation changes is important for making future projections of regional precipitation change. Stationary waves and zonal asymmetries play a significant role in the southern hemisphere winter circulation response to climate change. We have argued through both regression analysis and barotropic model simulations that the pattern of changes can be explained by changes to the Rossby wave source over the low-latitude South Pacific. Crucially, this underlines the importance of accurately simulating changes to the tropics in making projections for the extratropics. However, this leaves a number of unanswered questions, and this includes precisely what mechanism gives rise to the Rossby wave changes. Now, I haven't shown this in this talk, but I will note in passing that the Rossby wave change does not appear to be strongly correlated with either changes to the Walker circulation or the Hadley cell. Also, this work concerned CMIP5 models, and it would be of interest to check whether the latest CMIP6 simulations show similar results. Finally, I would just like to say thank you for listening, and do please get in touch if you have any questions. Thank you.